Okay, let's get to it. Points, lines, and planes. Why are we starting with these things? What the heck are they good for? Well, we're starting with these because geometry, like everything in mathematics, starts with a few basic elements and then builds its way up. Points, lines, and planes are going to be our basic building blocks in geometry. And in fact, they're so basic, we call them undefined. Well, how do we talk about it if we don't have a definition? We're going to agree as to what they mean. Why don't we just give them definitions? Well, it turns out there's something called infinite regress, which means if you were to try to define absolutely everything, it just never stops. A perfect example of infinite regress, if you have a little brother or sister, you may have heard them when they're just learning to talk and starting to ask questions, and somebody would say, "Oh, we have to hurry," and the kid would say, "Why?" "Because we'll be late." "Why?" "Well, we don't want to be late." "Why?" "Well, people will be mad at us if they have to wait for us." "Why?" That will go on to infinity. At some point, the child just has to accept the answer and not say, "Why?" Same thing here. At some point, you just have to accept we understand what these things are without a rigorous geometric definition. Otherwise, every time I used a geometric term to define one of these terms, I would have to explain that geometric term, and on and on and on, and we'd never get to a point where we agreed on anything. That's the basic nature of infinite regress. To avoid that, we have things which we just accept. Some of them are definitions, and there's only a few. The point is to minimize anything that you don't actually prove. We also have, in geometry, something called axioms, or postulates. These are statements about geometry which we don't prove. We accept them. They make sense to us, they seem reasonable, so we accept them and go from there, using these, what are called undefined terms, although we know what they mean. Defined terms and postulates, we can put together statements about geometry called theorems. But you got to start somewhere, and we will start with the most basic building blocks of geometry, which are points, lines, and planes. And now we got to do something really dumb, something I don't like at all. We define things in terms of what they aren't. Since there's no true geometric definition for points, lines, and planes, we can still give sort of an English description of it so that we know what the heck we're talking about. A point is normally written this way. It's described, represented this way. Point, boom, and we don't say too much more about it except that it has no dimensions. It has no width. I guess that would be width. Maybe that would be width and that would be length. It doesn't matter. It doesn't have either one. It also has no depth. We live in a three-dimensional world. It has no dimensions. It's mathematical. It's an abstract construction we use in mathematics. Obviously, there is no real thing which would have no dimensions. In mathematics, we postulate this thing called a point. We pretend they exist. And in mathematics, they do exist. You're just not going to find one laying on the beach anywhere. Lines. Again, the easiest way, we could say it's a collection of points. Well, we got this point here that we didn't really define, so yeah, let's continue on. This is undefined, but I think we all know what it is. A lot of you would say, that's a line. Yeah, you'd be close. That's actually what we're going to call a line segment, and we'll get to those in a minute. If you go like that, that is a line. It goes to infinity in both directions. That's pretty much what makes it a line. If it doesn't go to infinity in both directions, it's not a line. We have names for things like that. Don't worry, they're clean names. And then we have planes. That's probably exactly what you think it is. Not airplane, just plane. And we usually draw them something like this. But remember, this is just a representation. What's a plane? Well, technically we call it a collection of points. Remember a point over here? A collection of points. In 2 dimensions. A line is 1-dimensional. A point, no dimensions. Line, 1-dimensional. It has length, but no width. A plane, whoa, now we got 2 dimensions. It has width, it has length. It is not finite. We represent it this way. We show these boundaries here. A plane doesn't actually have any boundaries. It goes to infinity in every direction. I have drawn 4 ways in which to go to infinity, but in fact those corners are all directions too, and there are 360 points on a compass. The plane goes to infinity in all 360 points, but only in 2 dimensions. It has length, it has width, no depth. So now that we have these 3 basic building blocks, we can start using them to define other geometric objects. We have 3 things here. We're just going to agree. We understand what they are. No real geometric definition. However, we need one more thing. If we're going to have these basic things, then use them to build up to more complex geometric structures. How are we going to talk about them? I'm going to call this the point. Suppose I got more than one. I mean, if you only got one point, I guess we could just call it the point. But suppose I got a bunch of them. What do I call this? The point. Another point. This is that other point. Most people don't do that. We do it this way. Call this one A, and it's arbitrary. You can call this P. You don't have to go with the next letter in the alphabet, and they don't have to be in order. And we can call this one Q. This is point A, this is point P, this is point Q. Notice I used capital letters. That's normal. Maybe in college you'll see a lowercase letter used to represent a point, because in advanced mathematics sometimes you have to break the rules because there's just too much going on. You can't always stick to the normal conventions, but you won't see that in high school geometry, which you shouldn't. I'm always going to use capital letters, and I think your teacher will too. And every book I've seen used capital letters for points. So now we have a way to talk about the point. That's point A, that's point P, that's point Q. I think that sounds a lot better than the point, the other point, and the other point. What about lines? Well, suppose, since a line is a collection of points which goes to infinity in both directions, I would say we could put 2 points on the line, but the points are already there. We're just going to emphasize them by drawing a little dot and then labeling them. For instance, we'll put point A there and point B there. We could have another point here called C. When we label this line, we only use 2 points. So we could call this line, that's this one here, line AB. Okay. What about line BA? Could we do that? Most definitely. It goes to infinity in both directions. In a sense, a line is non-directional, or it has 2 directions, depending on how you want to look at it. There's no one specific direction for a line, so there's no reason that AB is any more valid than BA. Could we call it CA? Or CB? Or BC? Yes. Any 2 points on the line are sufficient to label the line. We could have called it BC. We could have called it CA. And on down the line. In fact, there are 6 different names we could use for this. Now, I'm not going to write them all down. What about a plane? Well, let's see here. We label the point with 1 capital letter. The line we label with the 2 points on the line. Since the plane is the next step up, and we can figure out what that means later, how about we draw 3 points on the plane and use that as our label. In other words, this would be plane A, B, C. You could just as well call it plane C, A, B. And there are 4 more permutations. Is that right? Well, I hope so. There are 4 more permutations. You could have actually 6 possible names for this plane. Label it any way you want, as long as you use the 3 points on the plane. For instance, plane P, Q, A. Nope, that's wrong. I don't see P and Q up here anywhere. So if you were to call this plane PQA, people wouldn't know what the heck you were talking about. They would assume you were talking about some other plane off somewhere that you can't see, which actually contains points P, Q, and A. So use the points that are labeled on the plane when you label the plane. Other than that, it's kind of up to you. Now, lines are going to be very important in geometry. They're important everywhere, actually. And right now, we're going to define 2 more types of lines. Remember, we had this line up here. This one goes in both directions. Well, I can draw that real quick. Thought I could. There we go. That's a line. Well, suppose it doesn't go to infinity. At least not both ways. Suppose it just takes off like that. More like a real arrow. It has an endpoint here, but goes off to infinity here. What the heck is that? That's called a ray. This is a line. This is a ray. How do we get a ray? Well, we just cut the line. Cut it right here. We throw out all this stuff here. Everything over here, just it's all gone. And what we got left is this. That's called a ray. Now, working with the line again, what else could we do to that line? Well, we could bend it, but we're not going to do that in this class. However, we could cut it again. Suppose we cut it right here. Get rid of all that stuff. What have we got here? Well, that's going to look like this, isn't it? This ray had one endpoint. Let's call it A. Now that we've cut the line over here too, we've got the original endpoint from the ray and another one, B. These 2 endpoints also give us a way to label this segment. AB. How do we label this? We said A, that's going to be confusing me because people are going to think we're talking about the point A and not consider that there's a ray called A. We just have to draw some arbitrary point over here. B. And now that's ray AB. So we have line AB. We can have ray AB. And what about ray BA? Would that make sense? Nope. That's no good. The first letter is always the endpoint, and the second one is the direction in which the ray takes off to infinity. You could say that the other point is the side of the line which contains all the other points. In other words, a ray is sometimes defined as a line cut with one point and all the points on one side of the line. In other words, I'm not saying that very well, but what we obviously mean is we cut it here with, say, cut it with point A. Everything on that, all the points on that side over there, that's the ray. If we cut it over here, all the points on this side would be the ray. In fact, if I wrote ray BA, what I would mean is this one. with B here and A over here. Yeah, I'm probably spending way too much time on this. But these are the very beginning definitional elements that we really have to understand this, and it's fairly simple. Well, maybe I'm spending too much time on it. It won't happen again. We could also write line segment. Well, almost anybody could have written it better than that. But pretend that says line segment. We would write AB. Could we write BA? Most definitely. You see, a segment doesn't have any particular direction to it. It doesn't go off to infinity in either direction. This one has two directions. So the line we can call AB or BA. The line segment, AB or BA. The ray, no. AB, and that's it. Well, this is all kind of a long way to do things. Having to write out line, AB, plane, ARC, line segment, ray. Too much work. Math types are fairly lazy. We love shortcuts. So, how would we actually write line AB? We wouldn't write the word line and then AB. We do it like this. It's a little shorthand. In other words, we just put a little line symbol up over the AB. Fairly graphic, almost primitive. Very easy to remember and use. For ray AB, well, take a while to guess how we'll do that. We just draw a little ray up on top. Boom. Ray AB. And line segment AB. Yeah, just put, that was intended to be a straight line. Sorry, that wasn't supposed to be a squiggly tilde or anything. That is a straight line. And by straight line, I mean line segment, of course. Now and then, throughout the year, you may hear me say line. I'll try to always correct myself and remember to say line segment, because, after all, most people, if you ask them to draw a line, will go like that. They won't put the arrows on each end to indicate, because they're probably not sitting in a geometry class when you ask them to do that. So let's take a look at what we've got here. We've got points, lines, and planes. Basic building blocks for geometry. This is how we represent a line. And a point and a plane. Now, when we label them, we do it this way. Line AB, ray AB, line segment AB. Or you could just say segment AB. Now, let's take a look at planes and some conventions we're going to use with planes. Not just in terms of naming them, but the way we draw, say, intersections of planes and lines. But first, I think we need a plane. And there's a plane. How would we draw a line on the plane? Well, that's pretty easy. We do it like this. And of course we could label it. Say line. Let's stick with A and B again. See how that works out. That line is in the plane. And if I draw another line up here, that line's not in the plane and really doesn't look like it's ever going to intersect the plane. Suppose I draw a line up here. And that's a segment. This is a line segment. This is a line segment. And if I put the arrows on here, boom. Now I can make it a line if I want. You can just see that line lies inside the plane, because we've drawn the whole thing inside the plane. This line, that's outside the plane. Simply because of the way we've drawn it. See, we've represented the plane as this finite well, actually, this kind of square or rectangle, doesn't matter. When we draw things outside of it, we're trying to imply that they're not in the plane. And working with infinite objects is obviously difficult, so we just have to use these finite representations and then go from there. And that's what we're doing here. So when we show a line intersecting a plane, this is the part of the line that you'd be able to see. This is the part that runs behind the plane as it intersects and then goes through. You couldn't really see it, so we just represent it with dots. And that's how you know all through this year in geometry and on standardized tests virtually everywhere. When you see this solid line and then it turns into dots, that means that this is the intersection point right here, and that this is behind the plane and this is on top of it. And that's true for lots of things. If you've taken any mechanical drawing, you saw these dotted lines that show the invisible lines, the lines that are behind the object that you're looking at. For instance, when you draw cubes, you see some of the back lines are drawn as dots or dashes because you couldn't actually see them if you were facing the cube. The lines that you could see are drawn solid. We may do the same thing here. So remember, when you see the entire line inside the representation of the plane, that means they mean to imply that the line is actually in the plane. When you see it like this, they mean to imply that the line is not in the plane. And when you see this, it's intended to imply that the line intersects the plane. Speaking of intersections, what happens when two lines intersect? Well, not much actually. But there is something you need to know, and that is two lines can only intersect at one point. The only way they can intersect at more than one point is if they curved around like that. And that wouldn't be a line. Lines don't have curves, so forget this part. You can't do it. It's just a straight line. Lines intersect at one point. Maybe I should redraw it over here so it's not so sloppy. One point is where they intersect. Now for lines and planes, here the line is in the plane, so you could say the entire line is the intersection. Over here you could say there is no intersection. Here it intersects at exactly one point. So lines may intersect not at all, in which case they're called parallel. They never intersect no matter how far out you go. We haven't gotten to that yet. But it's also a word that's used in English to mean about the same thing, so you're probably familiar with the concept. These are two parallel lines which never meet. These lines definitely are not parallel. They do intersect. In this case, you can have no intersection with the plane. The entire line could be the intersection with the plane, or it can just be one point. What happens if two planes intersect? Well, son of a gun, we just happen to have a picture of two planes intersecting right here. See the intersection? It's a line. Now, planes don't have to intersect. Planes can be parallel just like lines. It's possible for two planes to be lined up in such ways that they never intersect. They go off to infinity in all directions but never intersect. It's like two disks on top of each other, say separated by an inch or something, but if you were to extend that surface out to infinity, neither of the surfaces would ever touch. That can happen. Or they will intersect, and it doesn't have to be, this kind of looks like they're perpendicular. It doesn't have to be. You can intersect at any angle. The intersection will be a line. And when I say line, I mean a real line. I mean one of these that goes off to infinity in either direction, not a segment. It's represented that way. It kind of looks that way because we're using a finite representation of an infinite plane. So it looks like the line might actually be a segment. But it's not. That line is, that's a real line. Take it from me, that's a real line. In most all of these videos, we'll start with a very short introduction to the material, and then we will work problems. because that's what math is all about. That's what you're going to have to do on the standardized tests. And even if you weren't, math is about getting solutions. If that's not what you're doing, then you're not really doing math. That's the way I look at it. I admit I'm more into applied math than the heavy abstract stuff, but the way I see it, if you're not getting answers, you're not really doing math. Math is about solving problems. And that's what we're going to spend most of our time doing in these videos. But this first basic stuff is so important. I've actually devoted the entire video to just yammering. We'll do a lot more actual work later. I know it's extremely boring for the students to just sit there and listen to someone talk at you. You need to be more involved. If you haven't fallen asleep yet, I'd like to point out that what you're studying is called Euclidean geometry. Why Euclidean? Well, he wrote a book called Euclid's Elements, which, about 400 pages. First he laid out all the axioms. These are the things that we accept without proof, and I think there's about 11 of those. And then went from there. And he also laid out points, lines, and planes, and didn't actually define what they were. He just accepted that, hey, we all know what they are, so let's go from there. He didn't invent geometry. The Greeks didn't invent geometry. The results were known to the Egyptians thousands of years before the Greeks. Remember, the word geometry comes from geo, earth, metry, measure of the earth. The Egyptians knew how to do that. They knew the results. For instance, they knew that if you had a circle with radius d, then the circumference c would equal pi times d, which is the same as saying that the ratio of circumference to diameter is equal to pi. And they knew that pi was about 3.14. That's about, I don't know if they carried it out to any more decimal places than that, but they were aware of this result, and they could use it. They didn't know why, they just knew it existed. It's also true that they knew something about right triangles, something that we don't know yet, because we haven't studied it. But if we take the length of this and square it, and take the length of this and square it, add them together and take the square root, we'll end up with the length of this thing here. That is Pythagoras' theorem. Pythagoras is Greek and came long after the Egyptians. What Pythagoras did was prove the result about this hypotenuse here. The Egyptians just knew functionally that it worked out that way, and they used the result. If you see the difference here, they couldn't prove it was true. They just knew that every time they tried it, it worked, and they were willing to accept that from then on, it would always work. Not a totally stupid idea. In fact, it turned out they were right. It did always work. They built pyramids that didn't fall down. They surveyed the Nile River very accurately. They knew what they were doing. They just didn't lay it out in a logical construction that could be developed using deductive and inductive reasoning. The Greeks turned it into a much more abstract science. Many people throughout history have studied geometry just because they felt it sharpened their brain. Seriously. Working out logical proofs can be actually very good exercise and can keep you sharp. Benjamin Franklin, he liked geometry. Seriously. When Benjamin Franklin wrote, "We hold these truths to be self-evident," he was borrowing from geometry. In geometry, we have axioms and postulates, which we consider self-evident. We don't prove them. We just say, we consider these things to be true. We're not going to prove them, we just have to accept them. Otherwise, we end up in what I referred to before, infinite regress. Well, it's no accident that Benjamin Franklin chose those as the opening lines. It's the way he felt about it. This doesn't require proof. This doesn't require an explanation. This is known to everybody who's got half a brain. And then he went on from there. So you could say that, in a sense, the very United States government is based on geometry. Well, that's the end of this video. In the next one, we'll be covering the same subjects, but working problems, which is, as I mentioned before, what math is all about.